Welcome back, everybody, to the second part of session 2, standing between yourselves and lunch. And I'd like to thank you for coming back so promptly. I'd also like to welcome our candidates who have joined virtually. Hopefully, you're able to hear the talks. I'm not sure if you have access to Slido, but obviously, if not, then please do what you can to share any information or questions or thoughts. So we are continuing the theme of this morning, which is our novel formulations and process technology. And our first speaker of this second part of the session is Chris Gruenloh, one of my previous colleagues from GSK. Welcome, we get everywhere these days. Chris is a research fellow in the GMP lab of PPD clinical research, which is part of Thermo and supporting development and implementation of analytical solutions, for clients developing OI NDPs. As I said, he worked at GSK, I think, was it AdVary development we worked on, Chris, a long time ago, where he was leading analytical and CMC teams for treatment of asthma, COPD, and metabolic diseases. And his interests include delivery of biologics, respiratory tract, and better controlling sources of variability. And I think that's the subject of your talk today, around how we can improve Plume Geometry. So the title of Chris's talk this morning is entitled Plume Geometry, Examination of Processing Schemes and Inter-Analyst Variability. We can do better. Thank you, Chris.
Well, I certainly appreciate the invitation to be here today. It's my pleasure to provide the talk on this. So why Plume Geometry? There's probably a lot of skepticism out there regarding the value of this technique as an aerosol characterization method. In fact, a recent IPAC-RS survey, one of the respondents provided the following feedback, that system settings were more likely to be impacted by the instrument than actually the sample, which is a little bit concerning, I might say. Plume geometry has also been perceived for a long time now as being very subjective and/or analyst dependent. So why do we do this technique? Well, in short, because the US FDA requires it as part of the generic approval pathway for MDIs, soft mist inhalers, and nasal sprays. Now, if you look at some of the product-specific guidance out there, you'll see this sentence in terms of the requirements, and the key words have been highlighted there in light blue, and that is when you do plume geometry, there's an expectation to report the results based on a single delay time or a single image out of probably 75 or 100 from the whole actuation. Now, I note this because there's no such requirement for spray pattern, the sister technique, where the norm is to provide a time-averaged image. So what I want to cover today in this short period of time is I want to talk a little bit about the experimental background here, some sources of variability associated with this technique, and then I want to discuss some of the variables that we interrogated here, from processing scheme to inter-analyst variability. I'm going to throw in some bonus data from relative humidity as an environmental factor, and then we'll finish things up. So, lots going on in this slide. This is a relatively well-informed audience, so I'm going to skip a lot of the information here. What I want to focus in on are the 3 action steps that the analyst needs to take to affect this measurement. First of all, the analyst needs to select an image or image to process. If they want to select a single image, it's usually the one of the highest intensity. Number 2, they need to select the origin and where that origin is located within the software. 3, at that 6 centimeter distance, they have to tell the software where the outer edges of the plume are. And so they have to set what I'm calling arms as part of that process. Once they've completed these 3 steps, the software is easily able to calculate the angle and width. Okay, so my team at PPD, which consists of about 220 analysts that are spread across our Middleton, Wisconsin, as well as our Athlone, Ireland site, have been interested in sources of variability over the last couple of years. We've been investigating this technique, spray pattern, and some others. If we look at various sources of variability, within this particular experiment, we've controlled some and we varied others. So the ones we've controlled, the environmental aspect, we've done the experiment in a controlled temperature and relative humidity lab. The sample that we've used are 4 commercially sourced products, 3 cans each with 3 actuations per can. The equipment, all the testing was performed on a single automated actuator with a single Proveris spray view system. Okay, now we're getting into the fun stuff. This is what we actively investigated and varied. We used a protocol-driven approach in which we assessed the use of single image versus a time-averaged approach. We looked at 2 different locations by which the origin may be assigned. And then thirdly, we looked at 2 different processes in which you can set those outer arms at that 6 centimeter distance. Finally, we gave 3 trained analysts the same data sets and said, go ahead and process these so that we could evaluate inter-analyst variability. This slide, I want to further define things a little bit. So origin positioning, what I'm defined as the edge of the mouthpiece. The mouthpiece is here and quite literally right at the edge. That's to be differentiated from nozzle, which we've defined arbitrarily as 10 millimeters to the right, which would be closer to the actual nozzle of the MDI. Relative to the arm positioning, we used a 30% less than or equal to 30% intensity value that's provided by the software to guide the analyst as a way to set these arms. And since we have trained analysts who perform this technique day in, day out, we said, okay, use your best judgment, visually assess and place the arms. If we combine all this together in a testing scheme, we had 4 unique processing schemes. And the color coding here shows the variables that are being compared across each of these processing schemes. So you see in the green, we can compare setting the origin at the nozzle versus the edge, using a time average versus a snapshot, or using the 30% intensity versus visual. Okay, so here's our data. Please note that individual contributions of our 3 analysts are shown here as color-coded. I've also coded the drug product strength, so things would fit here. So if I say drug 2A, it's really Symbicort, low strength. So we've got Symbicort and Flovent as our drug products. The table above, I've normalized the plume angles that were measured according to processing scheme number 2. So if you look at the data set, starting off on the far left here, you'll see that, these plume geometry angles are all very similar and they have similar amounts of variability. There is a unique difference between the origin placement of nozzle versus edge, and this is purely a geometric effect. In one instance, we've got a 6 centimeter distance, in the other, we've got a 7. And the 7 centimeter distance with nozzle, you would get a smaller plume angle as you would expect. The interesting effects here are when we compare time average to snapshot, where we see a widening of the plume angle, but also a large increase in the associated variability. So in terms of all of our measurements, we're about 4% RSD with these guys, and once we get here, we're 12, 13% RSDs. Next, we looked at inter-analyst variability. So we've got the processing schemes coming down the y-axis along with the drug products. We've got the individual analysts, N equals 9, processings. From that, we looked at the average and relative standard deviations across the analyst. Within a certain processing scheme, we took a master average of the RSD to provide one number that can describe the variability of that processing scheme. So what we see from this is that the time-averaged approach achieved the very best inter-analyst variability, about 0.5%. When we jumped from the time-averaged approach to snapshot mode, the variability increased by a factor of 6x. And then when our well-trained analysts just visually placed those arms, the variability increased by another factor of 2. So I'm going to change gears a little bit now. This is some work that we presented at last year's AAPS FarmSci 360 in a poster in which we were investigating the relative humidity dependence on the plume angle for these 3 selected products. So we've got Flovin and Symbicort again, and we've added QVAR in this instance. So at these 2 temperatures, we varied independently the RH from 25% to 60%. And as you can see here, we have a very statistically significant impact due to relative humidity. Now, this is product specific, as you see, or product dependent, in that Symbicort goes in the opposite direction, but all of these were statistically significant. So wrapping all of this up, Plume Geometry, I think I've shown you today that we can certainly do better. The processing scheme will impact both the magnitude of the spray angle as well as the associated variability. We saw a 6x reduction in variability associated with using a time-averaged approach versus that single snapshot image. We saw basically a further reduction in variability if the analyst used a 30% intensity-based approach versus freely placing those arms. Finally, I've shown that by controlling the environment, you can reduce the source of environmental bias associated with this measurement. And concluding, stop blaming the analyst. The variability that's seen here is really probably associated more with processing scheme than anything else. So, understand your sources of variability and bias, implement appropriate controls, and that's going to increase the value of your data. Thank you, and I'd like to acknowledge some of my co-authors, Jenna, Carrie, and Karen, and I'd value any questions that you have. Thank you.